Okay, so let's do the second part of lecture number 9 on relativity, electrodynamics, and general relativity. As I promised last time, our emphasis here is formal. We're going to try to write electrodynamics in covariant notation. Okay, we got into that. We really developed the ideas all from seat of the pants arguments with forces, accelerations, and such. And now we want to see that we can assimilate all of that work into equations that are manifestly covariant. Okay, so let's do that. Well, the first thing we face is the electromagnetic field. I've written it as terms of E and B, and I know how E and B transform from one frame to the other. They satisfy this set of transformation laws. It looks like Lorentz transformations, but it's not quite. Okay, and it involves 6 objects that mix, not 4 objects. So it's related to Lorentz transformations, but it's different. It involves 6 objects. It's a 6-dimensional representation of the Lorentz group, like as we would say. Okay, it's not a 4-dimensional representation of the Lorentz group, and we have to sort of try to see how it fits more easily into the ideas of relativity related to 4 vectors and 4 tensors, and write it in a way where its transformation properties are manifest. These transformations look a little bit different. We have to see that actually they're just hiding some simplicity from the perspective of relativity, and we have to discover that. So how do we organize E and B into a covariant language? 6 components. How does it fit? Well, the x mu is the 4 vectors are 4 components. Won't do. Okay. What are other objects that transform simply under relativity? Well, those are the tensors, which I illustrated as the outer product of 2 4 vectors. Okay. But they're objects that depend upon 2 covariant or 2 contravariant indices. So the first one that came up was the metric tensor itself, G mu nu, and here we'll be discussing the electromagnetic field tensor. Okay. Well, if we write it as, we'll be looking into an object, F mu nu. It depends upon 2 covariant indices, and it has too many components, right? Mu can vary from 0 to 3. Nu can vary from 0 to 3. That's 16 components. We don't need all those components to capture 6 independent quantities. Okay, so there must be some special features of this tensor, but let's try to fit it into a second-rank tensor because it fits with some extra space left over, and we want to understand that. Okay, well, so I have E and B, two 3 vectors. So if I'm going to fit it into a tensor, let's think about the components of the tensor. Well, then certainly F00 must be 0. Okay, those are 0th order components. I don't have any 0th order components here. I have 2 vectors. So if it's going to fit, I've got to have F00 equals 0, and of course that has to be true in all frames. Okay, because I'm looking for covariant expressions. I could choose any frame to make this observation, and so it must be true that if F00 is 0 in one frame, it's 0 in all of them. Okay, so that's a constraint on the F mu nu that's going to be big enough, just the right size, to capture E and B. Okay, so let's look at that condition. Okay, that F00 is 0 if F prime 00 is also 0. Okay, I'm playing around with zeros. Okay, well, I know how, if this is a second-rank tensor, I know how it transforms from one frame to the other. I just have the coefficients of 2 Lorentz transformations, and I've written it down with the indices just so. And we're used to that. And I know what the coefficients are. I just read them off the transformation law for x mu. I know that L00 is gamma, L01 is minus V over C gamma. I know what L10 is. I know what L11 is, and such. Okay. I know the others are 1s or 0s, and I have them all written down. Okay. Okay. And so now I can look at F prime 0 0. Okay. And I can calculate it from the F in the other frame. It involves lots of other components of F. Not all of them, because because a lot of these coefficients are 0. If I'm looking at f prime 0, 0, then my Lorentz coefficients are L0 upper 0 and L0 upper 0, and then I have to sum over the lower indices to make the matrix products as shown there. Most of those are equal to 0. I've written out the ones that are not equal to 0. There's L00, L00, because L00 is gamma, right? And then and that involves F00. Then I get a term that involves F10, that involves L01, that's non-zero, and L00, that's non-zero. And then I get also a term that goes like F01, this guy with the indices backwards, and I get a term that goes like F11. So I just write it out. You know, I'm just trying to do a little game here of find the properties of F mu nu so that it could encompass E's and B's. I don't know that this will work, but that's something that is going to have to be true. And so I see in order for F prime 0, 0 to vanish, it must vanish because I don't have any entries possible for it. E and B, two vectors, and their components 0, 0 doesn't play a role there. So F prime 0, 0 has to vanish. So how do we get it to vanish in all cases? Okay. Okay. Well, I'm imagining that F00 is 0. I set it up that way in that particular frame. Okay. So I have to let's see. So I have I have two terms that involve the same coefficients, F01, F00, F01, F00. Okay. So it's going to have to be that the coefficient of that term vanishes, which means that F01 has to be minus F10. Okay, so that's written down here. That's what I learned. I have another term that involves different coefficients. Okay, and so that term has to be 0 on its own. F00 is 0. So I'm finding more. I found that F00 was 0, and now I find that F11 is 0, and I find that F10 is minus F01. Okay, well that was an easy exercise. Curious. I can do the same exercise by making a boost in the y direction or the z direction and find analogous statements. Okay, so I'll find therefore that F20 is related to F02 by minus, and similarly in the 3 direction. And then I'll also find the other diagonals. F22 and F33 must be 0. I made some progress now, huh? I've learned that the first row and the first column are related by a minus sign. Just collecting up all of these examples. Okay, I see that the diagonal of F is 0, and I see that the first column is negative the first row. Okay, that's the properties that F mu nu will have to have so that it can hold E's and B's. I have a little more work to do. Okay, I'll look at let me look at F02. Okay, and see how that transforms. Let's learn some more about it. And then I'll also look at F prime 20, the one that's related by interchanging columns and rows. I just write it, and I just write out the transformations, you know, with the Lorentz coefficients, which are non-zero, and I see that F prime 02 is related to F02 and F12, and F prime 20 is related to F20 and F21. But let's see. But I know that F02 is minus F21, so that applies to the left-hand side. And so I learned to get that in every case, it must be, okay, that I have that anti-symmetry on the right-hand side, okay, and I have it built in over here. Okay, I've already noticed that F02 is minus F01. Okay, I noticed that. And I'm requiring that statement be frame independent on the right hand side. So it must be that this other term has the same property on the interchange of the indices. And so I learned, okay, that F12 is minus F21. That will guarantee me that the contribution of this term and this term here are negative one another. They are the same prefactors, and so I can have that prime 0, 2 is the negative of f prime 2, 0. That's forced on me. Okay, and then I redo the calculation with boosts in the y and z direction, and collecting them all up, I'll see a more general relationship that for f upper ij, where I and j are Cartesian indices ranging from 1, 2, and 3, that fij is equal to minus fji. Okay. So, collecting everything up now, I found that f mu nu is in fact anti-symmetric. So let's count number of independent degrees of freedom of an anti-symmetric 4 by 4 matrix. Okay, well, the diagonal is 0 because it's anti-symmetric. It's minus itself, and the upper triangular block is minus the lower triangular block. And how many entries do you have in the upper triangular block? Well, you have 1, 2, 3, 4, 5, 6. Right. It's a 4 by 4 matrix. The four diagonal entries are 0. I have to just look at the triangular block above it, okay, and I just count 6 there. Perfect fit. E and B is 6 components. So we can represent. We're going to try to represent, therefore, E and B as an anti-symmetric second-rank tensor. The anti-symmetry is frame independent, right? We checked that already. We used that fact. Okay, that fact has been part of the construction, and that's just a feature of it. Okay, so now let me just write out the transformation law for f mu nu in the case that it's anti-symmetric. So I just do that. Nothing special. It's just wherever I see an f mu nu, and then I see an f nu mu, I'll just relate them by a minus sign to clean it up, to write it in terms of the minimum number of entries. And I do that, and here it is. Okay, and I look back here at what we discovered for E's and B's, and they're the same. Okay, they're the same. They're the same transformations. I have to move some of the C's around, you know, and I'll just put them into F appropriately. But I see the factors of V and gamma are same. I have a perfect match, and so I can fit E's and B's into the anti-symmetric tensor, and that's what I want to do. And I see that I can do that in 2 different ways. Okay, I can let F0i be E's, okay, and then the Fij's to be B's like that, or I could turn it the other way around and let the F0i be B's, and then the Ij's to be E's. Either way works, right? Okay. Either way of putting the E's and B's into the equation gives me the right transformation properties, the right way to do it. It's by convention that people call the case where you associate E's with F0i, the electromagnetic tensor, and the other case where you do B's first and then E's, we call that the dual electromagnetic tensor, like that. 2 different ways of doing it. Both ways give the same representation of the Lorentz boost. We note that F tilde mu nu is obtained from F mu nu by the substitution of E's to B's and B's to minus E. It's called electromagnetic duality, and we played with that in the text. Okay, we noticed that as a symmetry of the sourceless Maxwell's equations, and we played with it, right? In relativity, E's and B's mix, and this is a manifestation of that. Okay. Okay. So now we have E and B integrated into special relativity. In a sense, we're going to represent it through F mu nu, a 4 by 4 matrix, or a 16-dimensional tensor. In the case here, it's anti-symmetric, so it really only depends upon 6 components. Okay, and so I'll have to get used to it and play with it. And you have lots of opportunities to do that in the recitation sections. But let's do a couple of exercises and see that things work out. Let's write Maxwell's equations in terms of F mu nu and F tilde mu nu and J. Okay. So we begin with Maxwell's equation written in this old-fashioned way where the covariance of them is very, very obscure. Okay? And let's write it in such a way that the covariance is very, very clear. Okay? So what do I have to do here? The objects that I have at my disposal to rewrite Maxwell's equations with sources is the gradient operation. That's a 4-vector. I've written it here. I have F mu nu, and I have the 4-vector current density. And I want to just play with them and see if I can write this in a way which is manifestly covariant. Well, on the right-hand side, of course, I see charge density and current density, so I'll try to write a covariant equation with J mu on the right-hand side, the source. On the left-hand side, I see E's and B's differentiated by gradients in time, and well, the only object I have that's first order in gradients and is a 4-vector is the differential operated D, like this. So I write D sub nu, and then and then on the right-hand side I have one free index, that's mu, so I have to end up with one free index on the left-hand side, so I contract over the second index. Okay, remember, we've seen already that when you sum over a lower index and an upper index for two covariant objects, that you get a scalar, and so you can check that the left-hand side has the transformation properties given by mu, a 4-vector. So we'll try that. I'll put in the 4 pi k over c squared to accommodate the factors I see in front of me. Let's check that this guess is right. So I'll choose mu equals 0. So mu is fixed on both sides of the equation. I have to sum over nu, and that's shown here. I sum over nu like this. Okay. These are derivatives of the time variety. These are derivatives in the space variety. The time derivative hits f0, 0. That's 0. Okay. The space derivatives hit f01, f02, f03. That's components of the electric field. And so the left-hand side is just the divergence of the electric field. Aha. What's on the right-hand side? Just J0. Okay, that's just the current density. Okay, and now I just check my prefactors, which I've arranged correctly, so that it's just Gauss's law. Okay, so Gauss's law is one of the components of this equation, Maxwell's equation with sources, which is manifestly covariant. Great. Now, I asked you to check the other components, and you'll see that the other components make for you the Maxwell Ampere's law. And that's written down here. So check that as well. Same kind of arithmetic. I've done the hard work already now. Now it's all just fun. Now we want the homogeneous Maxwell's equations. Okay, so the right-hand side should be 0. The left-hand side should handle the divergence of B equals 0 and Faraday's law. And the obvious guess to do is just to write down the same kind of left-hand side we had here, except exchange F for F dual because that's another available anti-symmetric tensor, and set that equal to 0. I've already used F mu nu. That's finished. That's how that fellow contributes to Maxwell. But I have this other tensor available, and let's see what happens when I say that its 4 divergence is equal to 0. I have to sum over nu of gradient applied to F mu nu. So there are 4 equations here because mu can vary from 0 to 4. The nu's are summed over. So I'll choose mu equals 0 and write it out. Okay, and I do that here, just similar to what I did before. But now there's just an electric magnetic switcheroo, and so it becomes B's where I saw E's over here, and the right-hand side is 0. And so I get what I expect, that the divergence of the magnetic field is 0. That's a statement of the local absence of magnetic monopoles. Okay, and that looks fine. And then I can look at the spatial components of this general expression and see that it reproduces Faraday's law, and I ask you to do that. It's just pretty straightforward. But now you see you really made progress. Now Maxwell's equations are written as this and this. They are manifestly covariant. I've written them in terms of 4-vector four vectors and tensors. Special tensors, nice ones, anti-symmetric ones. Okay, the last thing we have to do is to write the Lorentz force law in a covariant form. What was the Lorentz force law? It was that the time rate of change of the momentum is given by the Lorentz force law like that. And I want to write that in a way that shows me that it's actually covariant. We enforce this, by doing explicit calculations. Let's get it manifest. Well, what do I have to play with? I have here I have momentum, and I know that momentum makes a 4 vector in relativity. I write it like this in terms of m times the velocity 4 vector. Okay, I write it as dx d tau, where d tau is related to dt by time dilation. I measure time on a clock moving with the particle. So in the lab, I see that clock dilated. Okay, and it's good to write it this way because this velocity, as we've discussed, is a 4 vector. dx mu is a 4 vector. d tau is Lorentz invariant. So if I'm going to try something here, the left-hand side should be the rate of change of the 4 vector momentum with respect to tau, because then the left-hand side transforms like a 4 vector. And on the right-hand side, well, I see e's, b's, and velocities. Well, the only thing I can do that for is to take something like f mu nu, that gets me my e's and b's, times u, which gets me the velocity here. Okay, like that. So I'm writing it in terms of 4 vectors and making sure that the indices match appropriately. There might be a question of plus or minus signs, which way to do f mu nu, and I've chosen it so that it works out. But that's something you have to fiddle with to get the right answer. And here's the charge. So I could write it out. Let's write it out for j for mu equals 1. Okay, so I put mu equals 1 into this formula. Mu becomes 1 on the right-hand side. Then I have the sum over the components of the 4 vector like this. So I have u0, u1, u2, u3. Okay, I watch my plus minus signs, and I write everything on the right-hand side in terms of contravariant vectors. So I have minus signs for the metric. Okay, and that's fine. And now I just put in there what's what's u naught? It's gamma c. What's f01? That's e over c. What's u1? That's this term, that's f11. F11 is 0. He's gone, right? So I go to the next ones, which involve u in the 2 direction, that's the y direction, and u in the 3 direction, that's in the z direction. So I have u in the y direction, which is a gamma, the 3 velocity, okay? And then f21, that's just the magnetic field in the 3 direction, b sub c. And so I'm just substituting away. But when I do that, I see that my velocity terms generate the cross product in the x direction. Okay, see I have yz minus zy. That's the cross product in the x direction. The factor of gammas cancel. Okay, this cancels this, and I'm back to the Lorentz force law as we wrote it down in a naive fashion, and then checked that it was covariant actually. So great. So we've succeeded in what we wanted to do. We have the Lorentz force law covariant, and we have Maxwell's equations written in a covariant fashion. That's just what we wanted. Okay. Okay. So that's all we want to do in this lecture in quantitative terms. Now we just want to say a few words about where we're headed in the course. There's lots more to do with E&M, of course. We want to really study the energy momentum and angular momentum carried by the electromagnetic field and stuff like that. We want to be able to solve using retarded propagators problems in radiation and such. And there's a lot of that in the textbook, and we'll do a lot of that in the recitation sections as well. So where do we stand? Okay, we've come a long way since we introduced Newton's laws and found that they had to be revolutionized by relativity. We made a lot of progress on the electromagnetic field. In Newton's world, the only degree of freedom was the charged particle, Okay, and E was given by a constraint. In Einstein's world, we have that the electromagnetic field is now a dynamical variable with 2 degrees of freedom, 2 polarizations. So we're much more sophisticated at that end of the spectrum. Okay, our treatment of electromagnetic field is now more complete than our treatment of particles. When we study collisions, we saw that in a relativistic setting, you have particle creation and destruction. Okay, you conserve things like charge and other quantities that might be conserved by the standard model, but you have particle creation and which are now possible because of the energy-momentum relation of relativity. Okay, we saw in some of our illustrations that there's pair production, okay, and that pair production occurs when you unify quantum mechanics with relativity, maintaining locality and causality. In fact, I promised you that when you do quantum field theory, you'll unify relativity with quantum mechanics, and you'll see that antiparticles are predicted as a consequence of causality and locality. That is, the theory of relativistic particles interacting with let's say electricity and magnetism, okay, have to include new degrees of freedom, okay, which are the positrons. When we moved from Newton's world to Einstein's world, we found that the electromagnetic field became a new degree of freedom, carried 2 degrees of freedom, okay, 2 polarization states for a traveling wave. And when we tried to unify quantum mechanics with relativity and maintain locality, we'll find that the degrees of freedom we started with are not sufficient, that we have to have antiparticles, and pair production is a consequence of that unification process. That's a wonderful result. Okay, and you'll study it when you do relativistic quantum mechanics. Okay, so we anticipate that at this point in classical physics, we're really deficient. We don't have an adequate description of matter. Okay, we know how to describe individual particles with relativistic kinematics, but there's much more that we have to do. We have to accommodate the existence of antiparticles if we're going to maintain a local description of interactions. That's going to be forced upon us. Okay, so we can look forward to doing that, and the discussion of the matter fields will be very analogous to the electromagnetic field. Okay, the world gave us the electromagnetic field, okay, in the 19th century, and matter field that will develop will mimic it. Will mimic it in many ways. Well, the matter fields will have different spin structure, et cetera, but a lot of the general properties will be similar, and we can't avoid it if those matter fields and the discussion of quantum mechanics of those fields, if we're going to maintain locality. If we're going to maintain locality, the whole idea of a single particle a framework is gone, okay? Because I can consider processes in which pairs are created. I can't, if I bring a lot of energy into a collision, I'm going to make electron-positron pairs. We show some examples of that, and that's forced upon me, not by some detail, but by a fundamental principle, okay, that the theory should be relativistic and local, and that the theory of a single electron isn't. It needs pairs. Okay, we have to go to a multi-particle description of the charged particles to maintain our fundamentals, and that's how we'll do it with fields for the electrons, not the old-fashioned Newtonian idea of an immutable particle. Okay, so that ends this part of the course. We're going to now, in this course, we'll continue with classical fields, and what we'll do next is classical differential geometry. I left off the word geometry. That's very bad. Okay, And we'll study curves and curved surfaces. We'll discuss intrinsic properties of those surfaces, the Gaussian curvature. And we'll discuss local and global properties of it. Local properties being Gaussian curvature, global properties being the Gauss-Bonnet theorem. And we'll touch on topology, and we'll do, we'll do some examples to pave the way toward general relativity. Because in general relativity, we're going to bring in the idea of covariance to classical differential geometry. Okay, follow the ideas of Riemann, and we'll be discussing in general relativity the equivalence principle. We'll discuss curvature. We'll see that tidal forces are key in there. We'll discuss how particles move in given gravitational fields. They follow the curves of minimal distance in the relativity sense. They're called geodesics. We'll write down those equations. We'll look for the field equations, the generalization of the idea that mass generates an attractive force field around it of Newton. We'll have to generalize that to a description of space-time, where the invariance is not just global Lorentz transformations, but local Lorentz transformations. That is, distortions, local distortions, and reparameterizations of the geometry of four-dimensional space-time. We'll discover black holes, and we'll discuss them. We'll look at Schwarzschild black holes, and a more realistic case of black holes which rotate, called Kerr black holes. We'll talk about gravitomagnetic effects, right? We know as a consequence of relativity that forces are going to be velocity dependent. Okay, that's property of relativity. It consumes all of the theories that you might want to make relativistic, including gravity. So we'll find velocity dependent gravity effects, and we'll see some very interesting ones in the context of the rotating black hole of Kerr. We'll discuss the ergosphere of Kerr. We'll discuss gravitational waves in the LIGO experiment, okay, and the first detection of gravitational waves. And then we'll discuss present problems, puzzles, okay. There's problems in gravity that are unsolved, deep problems. We don't know how to unify it with relativity. We don't know how to unify it with quantum mechanics. Okay, we know how to write it down in a relativistic fashion, but it doesn't sit well with quantum mechanics, and that's a puzzle that exists. Well, string theory, of course, might do that, okay, but there are issues there as well. Okay, so we'll want to say something about those puzzles. I'll talk about dark energy, say a couple of words about dark matter, the present problems in the field, and since they're puzzles and nobody has the answer, and we'll just present them. Maybe I'll say a couple of words about of gravity in the context of string theory, but not very much. That's really above and beyond what we're doing here. That's really getting into the quantum mechanics of a unification scheme that subsumes the standard model and gravity, and has properties which have yet to be elucidated. Okay, so I'll see you there.